Hello, welcome to my classroom. I am Nesli. In my first video about the Nernst potential, I have tried to explain how the Nernst potential of potassium is formed. May I remind you that Nernst potential is a theoretical potential, and the events I have described there do not take place in the body. Proper conditions to produce the Nernst potential can be provided in a laboratory with the aim to help us understand what Nernst potential is. So, what is Nernst potential? It is an electrical potential difference between the two sides of the cell membrane, and it is produced by a concentration difference. So, the concentration difference is between the interior and exterior of the cell. Nernst potential is an electrical potential difference produced by this concentration difference at the cell membrane. Please do not forget that all electrical activities take place around the cell membrane. So, what are the proper conditions to produce the Nernst potential at a laboratory? Number one condition is going to be the concentration difference. If we don't have the concentration difference, we cannot have a Nernst potential. The concentration difference is going to force the ions to move across the cell membrane, and it is also called a chemical force. So with this chemical, under the effect of this chemical force, the ions will try to cross the membrane. However, they cannot, because we need a second condition for ions to be able to pass through the membrane, and this is the presence of ion channels, specific for the ion that we are talking about. With these two conditions, the starting state in a laboratory experiment to produce Nernst potential is that there is electrical neutrality on two sides of the cell membrane. So the number of positive and negatively charged ions on the inside and outside will be equal, and there should be electrical neutrality before everything starts. So let us try to go over the knowledge that we have acquired from the Nernst potential of potassium, and let us try to exercise on it with another ion that is important for the electrical activities in the body. This ion is sodium. So, what were the conditions to start with? Electroneutrality on two sides of the cell membrane. Condition number one was the presence of a concentration difference. So, how is the concentration difference placed in living beings? The concentration of sodium is high on the outer side of the cell membrane and on the extracellular fluid, and concentration is low on the inner side of the cell. As we see here, we need to place the ion channels also, but to make it a simple drawing, I'm not going to place all the ion channels. Here is a symbolic ion channel, just to remind us that they exist all around the membrane, all over the membrane. So now we have all the conditions ready to produce a Nernst potential. The chemical force will be represented by a black arrow. This time our arrow will be pointing towards the inner side of the cell membrane because the chemical force will be pushing sodium into the cell this time. In the case of potassium, it was pushing potassium out of the cell. And then the electrical force this time will be represented by a red arrow in zigzag drawing. So, at the first moment, sodium ions will start moving to the inside of the cell membrane. This is going to create an extra amount of positively charged ions on the inside and an extra amount of negatively charged ions on the outside, which means an electrical potential difference is produced. The negative end of this electrical potential difference is located on the outer side of the membrane, and this is going to pull sodium towards the outer side of the membrane. So, for the arrow that is going to represent our electrical force, we can put the arrowhead on the other side here. Let's try to examine how these forces are changing as sodium starts moving into the cell. At the very beginning, a concentration force, a chemical force, is pushing sodium in. As sodium goes inward, a small electrical force is produced, and this electrical force will be pushing sodium outward. If we have a look at the net driving force, how are we going to find the net driving force? The net driving force will be represented by a green arrow, and as you see here, it is going to be smaller than the chemical force because some of the effect of chemical force is eliminated by the electrical force, which is in the opposite direction to it. We still have a force that is pushing sodium into the cell. The net force is still towards the inner side. So sodium continues to move inward. At this point, we need to remember the very important rule that the number of ions that move in to produce this electrical activity are very small to be able to produce a change in the concentration gradient. So as sodium moves in, the amplitude of the chemical force is not going to change, because, I'm repeating, the number of ions that move in is not big enough to cause a change in the concentration difference. However, the electrical force is going to increase. Electrical potential difference is going to increase because the number of ions that go into the cell is big enough to produce an electrical potential difference and to make it grow bigger. What happened to our net force? Our net force, represented by the green arrow, has decreased now. But there is still a net force that is pushing sodium into the cell. As sodium continues to go inward, these steps are going to repeat, and at a point we will reach an equilibrium condition at which the concentration the chemical force of the concentration difference will become equal to the electrical potential difference that was produced by the sodium ions moving into the cell. This condition here is called the equilibrium condition, and the electrical potential difference here is the Nernst potential for sodium ion. We can see that the Nernst potential is a potential produced by the concentration difference. In case of sodium, the Nernst potential is going to be with a positive side on the inner side of the membrane. A typical Nernst potential for sodium would be something like plus 61 millivolts. So what does plus 61 millivolt mean? It means that when the inner side of the membrane is 61 millivolt more positive compared to the outer side of the membrane, the net sodium ion movement is going to be zero. Chemical force will be pushing sodium in with the same amplitude of force that the electrical activity is pushing sodium outward. At this condition, we have an equilibrium. And there's no net movement of sodium, and the electrical potential is called the Nernst potential for sodium. If a typical Nernst potential for sodium is plus 61, what is a typical Nernst potential for potassium? It is something like minus 80 millivolts, which means that with the concentration difference that we have in this cell, the effect of chemical force can be stopped by an electrical potential difference equal to minus 80 millivolts. Or in other words, when the inner side of the membrane, let's draw a cell for potassium, when the inner side of the membrane is 80 millivolts more negative compared to the outside, this will stop the concentration force pushing potassium outward, which means the Nernst potential will be equal to the force of the concentration difference. As you see here, sodium and potassium, both of them are positively charged ions. Why does one have a plus Nernst potential and why does the other one have a minus Nernst potential? Because potassium, as we all know, is high in the cells. So for a positively charged ion with a high concentration in the cell, the Nernst potential is going to have a minus value. For a positively charged ion like sodium, which has a high concentration outside the cell, the Nernst potential is going to be a positive value. Try to guess what the Nernst potential for a negatively charged ion would be. The rule will work in the opposite direction. Chloride is high on the outer side of the cell. So when you have a negatively charged ion on the outer side of the cell, the Nernst potential of it is going to have a negative value. A typical Nernst potential for chloride is about minus 70 millivolts. By now we have learned that the Nernst potential is a function of the concentration difference. So it can be expressed in a formula which is called Nernst equation. Let us see our Nernst equation. This equation says that the Nernst potential of an ion in millivolts unit is equal to R times T over F times Z ln concentration outside over inside. In the books, you may come across a formula with concentration inside or outside as well. And then they will put a plus minus sign at the beginning of the formula, and you may get puzzled with it. So now, looking at the formula, I shall first simplify it by explaining this part, and then I will try to explain how the concentration ratio is related to the plus or minus signs here. R is the gas constant. So it's a constant number. T is the temperature in degrees of Kelvin. F is another constant number. It is Faraday constant. Z is the valence of the ion that we are using. So, because we have a lot of constant numbers in this part of the formula, it can be simplified. Here, during the simplification, we take the valence as 1, because most of the ions that we are dealing with during the electrical activities in a cell have a valence of 1. Sodium and potassium have a valence of +1, chloride has a valence of -1. So the formula is simplified according to valence 1, but there is one ion which is also important in the electrical activities, and it is calcium. Calcium ion carries +2 valence. So whenever we are referring back to the formula, we must keep in mind that the valence of calcium is +2. But right now, let us simplify this. For 37 degrees of centigrade, this value simplifies to 61. For 25 degrees of centigrade, it simplifies to 58. So, what will our formula look like when it is simplified? So when we simplify our Nernst equation, it will look like this. Plus minus 61 for the logarithm with the base 10 of the concentration ratio. Now we can concentrate on how this ratio is related to the plus minus signs there. I want to work on this by using the Nernst potential of potassium in a backwards manner. So what was the Nernst potential of potassium? It was something like minus 80 millivolts. This is going to be equal to 61 plus or minus, we don't know which one right now, times logarithm of the concentrations. We choose one of them. Let's say concentration inside over concentration outside. So, for potassium, the inner concentration is much bigger than the outer concentration. So the number, the ratio here is going to be a number bigger than 1. If you have a number bigger than 1, the logarithm of this is going to be a positive number. So now, from this part of the formula, we have a positive number. To multiply this number with 61 and to reach minus 80, we need to have a negative sign in front of 61. So, for potassium, if we want to make a formula, we must say that the Nernst potential of potassium is equal to minus 61 times logarithm concentration inside over outside. Now let us try to see how the formula is acting when we reverse the ratio. Again, we have a question mark about what sign we are going to place here. Plus or minus 61 multiplied by logarithm of this time concentration outside over concentration inside. Because the concentration inside is much higher than the concentration outside for potassium ion, this value, this ratio, is going to be a number smaller than 1. For a number smaller than 1, the logarithm is going to be a value with a minus sign. This value is going to be the same value from the first example, but this time it will carry a minus sign. So there is going to be a number here which will be multiplied by 61 to give minus 80 millivolts. So if this number carries a minus sign, then the sign at the beginning of our formula should be plus if we want to obtain minus 80 millivolt. So in most of the books they are writing concentration outside over inside or inside or outside, and they are balancing everything by putting a minus or a plus sign here, and they are acting on the safe side. And it's very difficult for the beginning to understand which sign or which concentration difference is going to be used. So if we look at the simplified formula again, for a positively charged ion, it was potassium in our example, the Nernst potential equation can be written as plus 61 millivolt multiplied by logarithm of the ratio concentration outside over inside, or the formula can be written as minus 61 millivolt times logarithm concentration inside over outside. We can use both formulas. The result of each of them is going to be the same. What about sodium? The same will apply to sodium because it also has a positive charge like potassium. But in case of chloride, this is going to be minus 61 millivolt times logarithm concentration outside over inside, or plus 61 millivolt with multiplied by logarithm of inside over outside. You can exercise on your own by giving numbers to see how this rule works. So I have repeatedly mentioned that Nernst potential is theoretical, but why do we need to learn it? Where are we going to use it? It has some use in the actual conditions in the body, and this some use is very important. One use of it is when we are trying to understand the resting membrane potential. This part I shall try to explain in another video. But here, in the last part of this video, I shall try to explain something else. This is when are we going to use the Nernst potential? When the ions are moving across the membrane. So, we said that there are two conditions for moving ions across the membrane. There has to be a force pushing the ion and ion channels. So, when these two come together, in which direction the ion will move? In this condition, we need to compare the directions and the magnitudes of chemical and electrical forces to understand the direction of ion movement through the ion channel. Let's give an example to make it more clear. Let's say we have a cell here, and then the cell, let's give a number to the membrane potential of this cell, inside being negative, outside being positive. Membrane potential in our example is minus 65 millivolts. What was the Nernst potentials of potassium and sodium? Nernst potential of potassium was approximately minus 80 millivolts, and the Nernst potential of sodium was approximately plus 61 millivolts. With all this information, we must be able to decide about the direction of ion movement when an ion channel opens. So, membrane potential is going to be our electrical force. Be very careful here. Nernst potential is the electrical representation of our chemical force. Under these conditions, let's imagine that channels for potassium are placed on the membrane, or they open on the cell membrane. The electrical force of minus 65 millivolt, how will it act on potassium? Because negativity of this electrical force is inside the cell, electrical force will be pulling the potassium into the cell with how big a force? 65 millivolt force. The second force is going to be the chemical force. The chemical force, what is it? High potassium inside and low potassium outside. We know that the chemical force will be from high towards low, and of course it's going to pass through the ion channels. And then we know its direction, but what is its amplitude? Its amplitude is equal to the Nernst potential of potassium, which is 80 millivolts. So if you look at here, Nernst potential is helping us to convert the chemical force into millivolts so that we can compare it to the electrical force, which is the membrane potential in the real case of a body. So, where do you think in this example, in which direction do you think potassium is going to move? There is a force of 65 millivolt pushing it in and 80 millivolt pushing it outwards. The net force is going to be outward. This is our net driving force, and with a force of 15 millivolts, potassium will be moving out of the channels if any channel is opened up under the conditions described here. Now let us repeat our example by sodium. If under the same conditions a channel for potassium is opening in the cell, the same cell. The cell has a membrane potential, negative on inside and positive on outside, and if channels, this time for sodium, this time for sodium open, what is going to happen? Sodium concentration is high outside and low inside. Now, the membrane potential, which is negative on the inside, is going to pull the positively charged sodium ions into the cell with a force of 65 millivolts. What about the chemical force? The chemical force will be from high concentration to low concentration, which in the case of sodium is from outside to inside. And what is the magnitude of this chemical force? The magnitude of it will be equal to the Nernst potential of sodium, which is 61 millivolt. The net force for sodium is going to be summation of these forces. It's going to be a big driving force pushing sodium inward, because in this case both of the forces, the electrical and chemical forces, both of them are towards inward. A total of 126 millivolts in this example will be pushing sodium into the cell if sodium channels are placed or opened at the membrane under the conditions of a membrane potential of -65 and a sodium Nernst potential of +61 millivolt. This is an example of how we are going to use Nernst potential when we are talking about many different conditions, when many different ion channels can open up on the cell membrane. Thank you for listening. Let's meet at another video in my classroom.